Hey guys, I got a question on this week's 3D printing tips, and this is kind of also the purpose of this channel. One is to kind of answer questions like this, as well as support my Udemy classes and things like that. So this is a great question that I wanted to split off into a little video. Generally, I don't get into this type of detail in the tips and tricks series because I don't want to dive that deep down the rabbit hole into exactly how the physics works and things like that. So in this video, we're going to dive a little bit deeper into this last week's video about the 3D printing enclosures and the benefits. So if you guys haven't seen that video, go ahead and watch it to understand. This is a little bit deeper dive into this last week's video. But basically, I was saying that Creality has these fabric and aluminum sheeted paneling enclosures that allow you to increase the temperature inside your enclosure, and that will increase. And then I told you guys that would increase the print quality. And the reason why that is that as the temperatures between your part and the extrusion temperature get closer together, the less warping you have. And the warping is caused by linear thermal expansion. And this right here is the conduction equation. So it's happening mostly by convection, but that's a little bit more complicated equation. It's basically like a little bit of a twist on conduction. So this is also very similar. You could think of it this way, but convection is a moving fluid. And so has to do with also flow and the viscosity of the fluid and things like temperature of the fluid, et cetera, et cetera. In order to determine this H value, which is the convection coefficient. So anyways, in here, so this is the conduction equation, and you have a couple variables here. K is the thermal conductivity of the material. How good is the thermal conductivity? So you have plastic versus like aluminum. Aluminum is very high, plastic is very low, right? So the conductivity is very low. The area, so this is the surface area of the, well, in this case, it's a cross-section area, but you can also think of it as far as convection, it is the surface area. So you can think of this more as a surface area. And the surface area of the part, so as the part keeps printing, the surface area gets larger. And then this is the temperature delta. So temperature 2 could be, it depends on whether you want the resultant to be a high or low number. You want to have a negative number or a positive number, then you switch these two. If you want to have a positive number, you switch, this one's higher than this one. If you want a negative number, you switch these two. So this would be like, let's say, if you want to know how much heat your part is losing, this would be the part, this would be like, this would be the environment, and then this would be your part. So if your environment is 30 Celsius, then you would put that here, and your part would be printing. And then this is the extrusion temperature. So the extrusion temperature could be like 180 centigrade. So you have 180 centigrade over here, and then you have 30 here. So 180 is larger than 30. This is going to be a negative number. And then distance is basically the thickness of the material. So you don't really have to think about this too much as far as this kind of pseudo equation that we're coming up to. So conduction depends on the material. Plastics are generally low and they're pretty close together, so you don't really have to worry about that too much. This is surface area. So the bigger the part gets, the more heat you're losing from the part. And then also it could depend as well as the surface area of that section of the print. So if the base, so let's say you go higher away from your printed bed, from your heated bed, and the size of the print gets bigger as it goes away from the bed, you're going to lose more heat there than the part that's closer to the bed. So generally for this, if you have an inverted structure where the base is bigger and then as it goes up it gets smaller, you're going to also have better performance that way. And the general idea of this whole thing is to decrease these two numbers, get these two numbers closer together. And you can see this is all linear. So what that means is that if you double one of these temperatures, then this number goes in half. And basically this is energy, or like joules, right, over time, which is power. Power is joules per second, joules over second, right? So this is basically wattage, or BTU, British thermal units. Same thing as like a HVAC system, right? So this is basically the energy that is coming out, the energy that is leaving your part and going into the environment, which you don't really want. You want it to stay in the part over time. And then if the energy does leave the part, you want to capture it to make sure it doesn't go into the rest of the room. So that's the other idea of the enclosure, is as the enclosure is stealing heat from your part, the enclosure is heating up, right? And then your hot end, as you're printing out more material, you're adding more heat into the part using your hot end with this new plastic. And also, you're adding heat into the part with the bed. So the bed is adding heat to the environment, and the part's also adding heat to the environment as the environment is stealing the heat, because the heated bed is going to be hotter than the environment, and the part is going to be hotter than the environment in general situations for general consumer grade printers. Right? And then this is the linear expansion equation. So you can see here, this is the delta length, which means the change in length. And then the equation is very simple. So you have alpha here, which is basically the linear expansion coefficient. Plastics is generally pretty low, but you'll have different coefficients depending on the plastic, right? So for example, the reason why ABS is quite a bit harder to print than PLA and things like that, number one is that you have to print at a higher temperature. It has a higher glass transition temperature, as well as it has a higher linear expansion coefficient. So that means per unit change in temperature, it'll expand more than other materials. That's also why it makes it so difficult to print, right? So you want to look at what material you're printing and look at the linear expansion coefficient, and then that will generally tell you how much it warps. Also, you have to take into account the printing temperature, because that printing temperature would be, for example, the T2 or T1, however you have the equation set up. So the higher that you're printing the material, generally the bigger the difference in the printing environment, right? And that's what you have here, the change in temperature. So if you're printing ABS at 230 Celsius and your environment is at 30 Celsius, that delta is 200 Celsius. So that's 200 times these, right? If you cut that in half, let's say you cut it to 100 C difference, then this is now half. The linear expansion is half, which means that it's going to shrink, it's going to warp half / shrink half of that. And also you have to account that your bed has some sort of force that's sticking your part to your bed. So if you half this, it might be enough that your bed has enough give to it that it will hold the part down to the bed, right? And so that's what you see here on this equation. So it all has to do with it all has to be relative, right? And the person that asked the question was asking if there's like an absolute number that I can give. And as you can see with these equations, it's all relative. So if you're printing out in like a garage, or I have some printers in the shed, they're all resin printers, and my FDM printers are in the garage. And the garage, now we're in winter, it's raining like crazy outside. And in California, West Coast of United States, right now it's getting down to the 30 Fahrenheit, so close to 0 Celsius. So getting to 0 Celsius at night, and that garage is not much warmer. It does have the hot water heater in it, but it doesn't get much warmer than that, so maybe 10 Celsius or so. If I go from 10 Celsius to 20 Celsius, there's going to be a drastic increase in print quality as far as warping control and dimension control. So dimension control also has a lot to do with this as well, because as you see here, there could be the difference here is the linear expansion. So if you're printing at a lower temperature, the part after it's done, after it cools to your regular day, room temperature that you're using the part, it depends also on if you're printing the part in 10 Celsius weather and you go into standard room temperature, let's say this 25-30 Celsius, your dimensions are going to be off, right? Your dimensional stability will be off. So the closer you are as well to that room temperature, also the better you are. Or you could always calibrate that in with scaling though in the software. Anyways, so that also has an effect. So anything helps. So increasing from 0 Celsius to 10 Celsius is could be as beneficial as going from 200 Celsius to 210 Celsius, right? So you'll have quite a bit better. You could have a better improvement at the lower temperatures than you do at the higher temperatures, because it could be the difference of all parts failing. So like you can't get anything to stick, or it's just warping, and all parts are just not usable, to some parts working or all parts working, right? With those particular settings and those particular materials. And then also, as you can see, it's definitely temperature. It's a material dependent, right? It depends on the linear expansion coefficient of that material, which is alpha. And there are websites such as Engineering Toolbox that you can go and find that kind of information. Next thing that I talked about on there is some of the downsides of having an enclosure. So one of the downsides of having the enclosure is also another thing that I wanted to talk about really quick about the enclosure temperature is it also keeps the breeze from coming in and causing cold spots on different sides of material. If you have a cold spot on a different side of material, it can cause that side to shrink more than the others, and that can amplify warping and cause a part to fail on one side and be okay on others. So that as well, it just makes it more of a homogeneous, like very controlled environment, having an enclosure. That's why a lot of printers nowadays have enclosures, is to keep it more stabilized and to drastically increase your performance and dependability of the printer. So the next thing I want to talk about is the possible failure with having these aftermarket DIY enclosures, and that is that the printers are not rated for these enclosures. And what happens is if you heat the enclosure up high enough, depending on the printer and the settings, again, it's all relative, you can have possible skipping steps of the stepper motors overheating, right? And as I was explaining in the text, which I now decided that it was a good enough question to make a video follow-up, as you heat up the enclosure, these motors are also going to heat up, and they could exceed their insulation rating because stepper motors themselves get hot. And some printers have ways of getting around this by having lower powered stepper options on the stepper drivers for the settings in the software, or they can have more efficient stepper drivers that don't heat them up as much, or they can have active cooling, water cooling, something like that. They could have the way it's mounted to an enclosure can allow for that to happen, the design from the factory, if you're using it using the native design. But if you take it out of a normally open printer and you move it into some enclosure like this, and you heat it with a bed slash hot end slash part, or you also add a active heater as well to add with a heat exchanger that's blowing past a PTC or something inside the enclosure to heat the enclosure up. The things are that you're exceeding what they planned on happening with the initial design. If they never designed it to have an enclosure, or that particular model, they never designed to have an enclosure. So he's asking about some absolute values for that. And obviously, like I said, it depends. It depends on all these different settings, the stepper driver settings, how the stepper driver is mounted, what it's mounted to. Is it mounted to plastic, or is it mounted to metal, right? For example, you can have the Prusa Mark III was my example, which has it has stepper motors that are bolted to PETG. Now PETG, the thermal conduction coefficient is low, right? But yet, even in a standard environment, when normally and they use a very small stepper motor, so it doesn't have very much surface area. The surface area is low because it's not very long, right? And so it doesn't have as much area to pick up the heat from that stepper motor. And also, by standard, they do not have any sort of way of increasing that area as far as from the factory, such as adding a heatsink. Adding the heatsink will increase the area, right? So they do not have that. And they don't skip steps, right? Now, they just released a enclosure, and I haven't heard whether it skips steps inside the enclosure, but I'm thinking that the reason why that happens is one of two things. Either they have the settings set up on the stepper driver that allow it to use less power, and maybe like a silent mode or something like that, or they are using high temperature tolerant steppers, right? One of those two things, or possibly a combination of those two things, right? And what are these different temperature higher temperature tolerant steppers. So a lot of people don't know about these, but you can have a printer that that's similar size but designed to be in a hot environment, last at way higher temperatures. So I gave an example of my Tronxy X5SA. It was never designed to have an enclosure around it. I put it inside an enclosure that was similar to in that video, like a Creality with a fabric body and then aluminum on the inside. And then I put in an active, I think 300 watt heater, and then had the bed up to 100 Celsius, and also the hot end printing ABS, right, at 230C. Now I think at maybe 40C or so, maybe 45C, which is like 110, 120, something like that, 130, I started to have steps skipping. So what I did to keep that from happening is I applied Heatsinks. I still saw skipping steps, and then I took out the heater. But I was just running the heater on full blast. Another way that you can get around this is by having a temperature controlled environment, so that when you see it happening, you can lower the temperature inside there or change a couple different variables, such as, like I talked about, the step settings, stepper drivers, stepper motor size, area, right? This area, what it's attached to. So increase the thermal conductivity of what it's attached to allow it to pull heat away from the stepper motor, or just in general turn down the ambient temperature, right? And so those are some different ways. So the Tronxy was failing around there, but my Bamboo carbon X1 carbon from Bamboo Labs is rated for 60C continuous use, which is 40, 50 degrees Fahrenheit higher than where my Tronxy was failing. And it's like, okay, well, these are both 3D printers, but they have two different failure modes. One could be that they have better conduction, and then this was after I modified the Tronxy X5SA. And originally, how they had the two attached was similar to the what's it called, the Prusa, right? Which was, it had acrylic pieces attached to the frame itself. And I actually found under normal operation in a hotter than normal environment, for example, California summer inside of a room, it was actually skipping steps with no enclosure, right? Because it was bolted to acrylic. Acrylic has a low thermal conductivity, and the heat had nowhere to go except for concentrate inside the motor, and then just run away until the motor couldn't handle it anymore. So what I did is I took the acrylic and I copied it to aluminum mounts and mounted it with aluminum. And then that issue basically went away for all room temperature printing, no matter the climate at that time. So even printers itself that aren't rated, and you could tell the engineering time that has gone into something by having the rating for that temperature, the ambient temperature, right? Ambient temperature rating, because I believe the Tronxy X5SA did not have one, right? Anyways, and so those are like one modification that I did to increase the thermal conductivity that got rid of that issue. So just because you've started skipping steps, decreasing the temperature is not your only solution. There are other solutions, right? And so let's go ahead and talk about some different stepper motors. So here, the most common is like the LDO motors, and they have these high temp, and you see HT, right? High temp, and then I think they also have it coded inside of the part number. And these are very common on like the Voron DIY kits. And the reason why is that they have a class H, which is rated at 180C, and we'll talk about the 180C. Basically, the 180C is like the max temperature that you can have. So that's these two, 40 plus 15 plus 125. So that means that the motor can max hit 180C before you have failure, right? And so these are super high temp, the highest that NEMA has in their classification for their insulation. So you can see here they have A, B, F, and H. And so these are very, very high end stepper motors here for high temperature applications, right? But still, that's 180C is not environment temperature. Environment temperature. It is the temperature at which the you have the conduction happening. So this K, right? And then also how much contact area you have / surface area of the material, how long the stepper motors are, the airflow that you have inside the system, and then if you have any passive cooling options, heat sink, active air, water cooling, etc. Or you have let's see what we're looking for. Or you have a special stepper driver where you are modifying the stepper driver settings, right? And you can see here that if you go to their website, LDO, and you type in, 42 millimeter stepper drivers, which are NEMA 17s, right? So NEMA 17s here, they sell the 42 millimeter. The 42 millimeter is the length, right? And you can see here that they're specifies an ambient temperature of -20 to 50, and I think that that's like a standard ambient temperature rating with, like I said, some of those things satisfied and possibly some of those things not satisfied. It depends on how they come up with the rating. But the actual rating is the rating that you can see here on the drawing, which is it can reach 180 Celsius without having issues with the insulation, right? And then you go to something else like a printed solid here, like an E3D. This is a slim line, right? You go to their drawing, and here on the drawing from the printed solid website, it doesn't have any talk about what insulation class it has. As you can see, you can search through here. I searched very briefly, but I didn't see it. Maybe I might have breezed by it, but I don't think, there is no mention of the class of insulation. So you could have something like this that has no ambient temperature rating or class rating. And then I happen to go to E3D's website and then look up their electrical parts and their motor drawings. And then I pulled up the slimline motor drawing. And you can actually see here, it is a class B insulation rating, which B has a maximum of 130. So that's a 40C difference, right? So that's a 40C maximum increase in temperature versus the 180 class. So this is like a lower temperature rating, but probably not as low as a standard low grade, maybe not even defined stepper motor, which could be like 105 temperature increase. And then talking about the temperatures for the enclosure that you should be shooting for, generally the rule of thumb is somewhere close to the glass transition temperature. So I found this website, it's pretty cool. Make Shaper. I'll put this in the description. Again, you have to look for something that works best for you, but you guys can try this. So here you can see here's the legend of the symbols. So printing temperature, and then you have bed temperature, which is this guy, and then the glass transition zone. And the glass transition zone is when things soften and start to get a little weird, right? So generally you do not want to, and they'll start to soften. Now generally you do not want to pass that unless you're doing something like flexible materials like TPU, which you'll see the glass transition temperature is actually lower than room temperature, right? And so you see here ABS, we're printing at 210 to 240, heated bed at 80C or more, and you can see glass transition temperature is 105. So usually your target is to have the ambient temperature up to that glass transition. So normally if you have a heated bed, you can heat it up to like 100C or so, and then heat the chamber up to 100C, right? Same thing in PLA, 60C, that's why bed 60C. You see how these kind of coincide here, right? PETG, 88C. And so here up to 100C, the reason why they're going past a glass transition is that the part will cool down, right? The bottom will just maybe be at that temperature, but the environment is sucking the heat out of it, right? So you might have to mess with this guy a little bit and see where your temperature of your enclosure gets. And but generally you don't want to have the bed exceed the glass transition temperature, just in case you don't want that bottom layer to start to get weird and come undone from the bed, right? You can see here TPU, it says like below room temperature, but still 40 to 60C. It doesn't really matter, you're past the room temperature anyways. And you want to get closer to this printing temperature to lower the thermal expansion, right? So here PHA 50 to 60 C. So we have the bed at 60 C, right? And then try to heat the chamber to 60 C. So, but you don't want direct contact of the part to be past that 60 C. So generally the bed is at the glass transition temperature, and then you use other means to heat the chamber, right? You either use active heating, such as a heater, or you just have the enclosure insulated as best as you can. And with a 60C bed and with your hot end at this temperature printing, it's just whatever the chamber is what it is. And you just insulate it to the best you can to prevent heat loss by building one. Or you or another one that I didn't talk about is you pick a time of day that the ambient temperature is the hottest. For example, me, I usually print at night because that's the time that I'm home, not at work. And most of the time I print for work, so I'll be at home at those times printing, and it's probably the worst time of day because it's the coldest. So you can wait till midday where it's the hottest to start the print, and you can get better performance that way. As I said here with this first image, these two are already closer together. And so as that heated bed heats up the chamber, it's going to heat up that chamber hotter because these temperature differences aren't as much, and so you aren't going to lose as much heat to the environment from the enclosure, right? Or whether it's an enclosure or not, because like I said, an enclosure at 0C versus freezing versus a enclosure versus no enclosure at 30C is a big difference, right? So you can also pick the time that you print around those high temperature parts of the day, right? And then also the maybe even in a place where you heat the room instead of just heating the enclosure itself, right? So inside of a house or something like that. But obviously you have some smells and volatile organic compounds that come off of stuff like ABS that could give you headaches and cause some serious health problems if not dealt with. That's why most of my printing is done in a shed outside or inside the garage where it's got proper ventilation. And proper ventilation, when you have a hotter building and it's colder outside, obviously leads to a colder room. So that's something that you also have to take into account. So that's about as far deep as I wanted to dive into this subject. Obviously, there's a lot more to talk about in the physics and things like that, and more of the analytics on that. But I think that this covers it quite a bit. So let's go ahead and go over a summary. Print at the hottest time of day. Basic enclosure can drastically increase your printing performance and dependability, and the better design of the enclosure, which is more insulation with a higher R rating or something like that, if you build one, the better off you're going to get. But there are limits, and those limits are your design of your printer. If your printer was never designed to be put inside of an enclosure, and that is what type of stepper motors does it have, what is the insulation class rating, what type of cooling systems do they have, what type of airflow inside your printer, how long is your stepper motor, what kind of stepper drivers and stepper settings does it have, etc. Right? And those can be remedied by increasing the length of the stepper, increasing the temperature rating of the insulation, such as the LDO high temp steppers, changing the stepper settings or changing the stepper drivers, and increasing the area of contact or the thermal conductivity of the material that is attaching the motor to the frame. So changing that from plastic to something like aluminum or copper. Or adding active cooling, such as water cooled, or passive cooling, which is something like a heatsink that drastically increases the area of the printer. And then what are some temperatures that you're looking to try to heat the enclosure up to? Usually the glass transition temperature of the material, or close to the bed temp that they are asking for the material, right? And those are my basic suggestions. And that's the summary of this video. I'll see you guys in the next one. Any questions at all on any of these tips and tricks, go ahead and leave a question in the comments. Thanks.